All right, this is a little lecture about passive solar heating systems. For heating buildings, we really only need low-grade heat. We need energy, and it has to be not a high grade of energy like electricity. So how do we get that? Do we get it by burning hydrocarbons, burning fuels, producing carbon dioxide, or do we get it from the sun, which is free, which has no pollution, no greenhouse gases, no negative climate change impacts? All right, we're going to start with the idea that if you're going to collect heat from the sun in a building, then you have to point the parts of the building which collect the sun towards the sun, and so you have to know where the sun is. And it turns out that the sun is, in the wintertime especially, mainly over in the southern portion of the sky. And so the maximum winter solar radiation comes when you point the glass or the collecting surfaces that you're using, the apertures, we call them solar apertures, towards the south. As you move away from south, the annual seasonal solar heating performance goes down. That is, the amount of radiation that you can collect through that aperture is going down as you move away from south. Now, in a temperate climate, you can see the diagram on the left. This comes from Sun, Wind, and Light in the strategy number 43, rooms facing the sun and wind. And it gives a design guideline for temperate climates. That's most of our mixed climates in the United States, for instance, of about plus or minus 30 degrees. And what you can see is that let's take the direct gain and Trombe line there. That's the most common, direct gain would be the most common type of solar heating system. That as you move about 30 degrees off, you only lose about 10% of the annual heating energy during the winter season that you could be collecting. So that's not too bad. If, however, you're in a very cold climate, like say Minneapolis, then every little bit, every unit of solar radiation is going to count. It's going to be important. And therefore, we're going to have a tighter recommendation. In this case, it's showing about 10 degrees either way from south. And then at the other end of the spectrum, you might have a climate like Eugene, Oregon, Seattle, Washington, the Pacific Northwest. Those are cloudy, mild, long winter climates where there's a lot of radiation over a long period of time, or let's say less radiation than if you had clear sky. You look up in the sky, and a lot of times you can't see where the sun is because it's occluded by the cloud cover. So in those cases, we can relax the orientation a little bit, say up to about 40 degrees either way from south. And you can even see that if you face your orientations southeast and southwest, that you're still getting perhaps up to 80% approximately of the heating energy. So by the time you do that, it also has some advantages that now you're collecting heat from two sides of the building, not just from one side, even though the apertures end up having to be bigger to collect the same amount of energy. So here's a building, the Red Rock State Park Visitor Center in Arizona. On the left-hand side, you can see the north elevation, if you can call it an elevation. That's the entryway, and you kind of sink down through these stairs. You can see it's built into the earth, and you don't even see a window there. So there's nothing to be being cooled off and losing energy from the cool north winds, and it's using the earth to shelter and protect and insulate. On the south side there, on the right-hand image, you can see that the apertures that are collecting the sun are actually in a curving wall. So the point of this really is that the orientation is not so strict, particularly in a clear sky climate like um, Arizona there. It's not so strict that it has to face due south. You have some flexibility as a designer. Okay, here's a really interesting and wonderful kindergarten by the architect Olivia Schimmick in Austria. The top image shows the north side and the bottom image shows the south side. So you can see the difference in the size of the solar apertures, the amount of glazing, solar collection, and so forth on the south sun-facing orientation. And then on the north-facing orientation, the windows are sized primarily for view and daylighting. It's also got a really interesting zoning strategy we'll see in just a second. On the south side, you can see what behind that big double height facade are two sets of children's classrooms. They call them children's houses. And at least on the lower level, they can come out into covered, shaded play areas. And then on the right, you can also see that kind of sloping glazed roof. That's a semi-protected outdoor play zone. Up on top, you can see active solar collectors. Those are actually photovoltaics, and some hot water collectors also. So here's the section. You can see where the PV roofs are. That's an open circulation and atrium section. So it's daylighted. There's passive solar heat. There's also active solar hot water that's heating the domestic water for use in sinks and restrooms and so forth. And then PVs that are making electricity combined with thermal collectors, which are actually using the sun to heat water. That's more of an active solar system. So this is a hybrid active and passive building. Down on the lower left, you can see that outdoor semi-protected play area, and that they can bring shading into play for the warm season, or retract that shading to get more sun coming in. And you can see it's still open on the end, so it's really an outdoor buffered kind of a space. On the right, you can see the entry into the circulation and the massive concrete walls. Is that concrete? Yeah, no, that looks like wood actually. Interesting. Okay, so there's concrete mass in the building also, you can the floors and in some of the structure. One of the really thing that's interesting about this is the zoning. So this is an example of heating zones. And so you can see where the sun is in that upper right diagram. So we have the terraces as a indoor, outdoor, in between kind of space. Then the children's houses, that zone is a series of what we might call classrooms. There's a core, which is mainly circulation, storage, restrooms, and so forth. Each classroom has its own private little restroom for the kids. And then the passageway or the circulation zone, which has stairs and corridors. Right? And then what they call the service block, which is offices, copy room, meeting space, and so forth, primarily for the faculty. On the right-hand side, you can see that glazed outdoor pavilion, another one on the left-hand side, and in between a sun space, which is now that instead of being open in the end, that's a fully enclosed but unheated space. In the sun space, we'll get to see what that is in just a little while, but that's a specialized form of passive solar heating. So the point of all this really in the heating zones is that the needs for heat can be zoned so that you put the things that need the most heat on the side that has the sun, and you put the things that maybe need the least amount of heat away from that. And in any building like this, you can see there's a series of zones or a series of rooms going from north to south. So some rooms get heated themselves. Then you organize the section. So for instance, that passageway zone gets some solar heating from above. And the service block, because it faces north, it has to borrow heat. So we're trying to say what are the needs for each kind of space? And let's give the best heat and the most access to the sun to the kids. There's little kids, they're sitting on the floor. It's cool there typically. And they're just lower down in space. And as you know, warm air rises. So that's a nice place to put them. A few more images. You can see the outdoor spaces, in semi-outdoor spaces, I'd say, with shading sails partially employed there. And it looks like some form of insulating shades also on the upper left. So that's, I would say that's probably makes sense to have in a sun space, but you could also have it in an outdoor space, I guess. Images of the circulation space. And you can see on the right kind of shading structures with photovoltaics up above for making energy. And this is a little bit early in the process of the construction, but one imagines that the vines grow up on that and make a really nice shading layer. So here's the notion of the heating zone criteria for the solar kindergarten. And so you take a look at what are the different occupancies and then what are the needs of those occupancies. Do they need more or less temperature, and how long is that occupied. So if it's only occupied for a short amount of time, for instance, like walking down a hallway, think about the stairwells in the art and architecture building, you can tolerate a cool temperature or a warm temperature for just a few seconds as you move up and down between floors or you go out into the circulation zone. But if you have to be there for a long period of time, then you're less likely to want to have that extreme level of variation. So that gives us a strategy then for whether the heat's being captured in the space itself or whether it has to be borrowed from another space. So in this case, the core might be doing some borrowing and certainly the surface block is doing some borrowing. Neither one of those has direct access to the sun. So our radiation is varying by season and by orientation. So these two graphs are really about illuminance, that's the visible spectrum, but essentially the radiation or the long wave portion of the spectrum follows approximately the same patterns that we see here. And I'll show you one for an annual radiation in just a minute, but this is the one by orientations that I could find right now. And so this is for Phoenix, and on the left-hand side you see December, on the right-hand side June. So notice that if I'm over in the winter, that the south orientation is actually collecting more sun than the horizontal. And the south orientation is collecting significantly more than the east or west. And the east or west are really biased towards one portion of the day. So you see the east has more light, more heat, more sun in the morning, and then it falls off to be approximately like the north in the afternoon. And the west orientation would be the inverse of that. On the other hand, if we look at June, now we're in summertime in Phoenix, the horizontal has a huge amount of sun. The sun is up high in the sky. It's beating down on the roof, or it's beating down on any horizontal surface. The east and the west are similarly extreme, but not quite as extreme as the horizontal. And certainly in the morning, the east is extreme. In the afternoon, the west is extreme. And then look down at the south. So the south is now has less radiation, less illuminance and intensity than any other orientation, except for the north. So the question then becomes, where do we want to point our orientation? If we want to be collecting heat, then we want to be pointing it towards the south in the wintertime. If we want to be avoiding heat, then the south is not so bad. The north is pretty good. And certainly we want to pay extreme attention to shading on the east and the west, while we want to avoid placing any apertures, if possible, in the horizontal, and you can see why. This is a graph of transmitted solar radiation. This one is for Knoxville, Tennessee. And you can see orientation across the months. So this doesn't have time of day, it just has seasons. And once again, the big one in the middle of the summer is the horizontal. So we want to avoid orienting that way in the summertime. And it doesn't really pay off to orient that way in the wintertime. On the other hand, the south is pretty good. It's high in the wintertime, low in the summertime. So that's where we want to be pointing our solar apertures. This is a housing complex in Denmark by Van Kunsten. And on the upper left, you can see the south facade. On the lower left, you can see the north side of the building. And then on the right-hand image is a close-up of the living spaces along the south side. So once again, you can see this kind of fundamental archetypal orientation of south versus north, particularly at this high latitude climate where in the wintertime, the sun just blips over the horizon on the south side of the building. So all of the living space, the kind of outdoor garden space is on the south side. The terraces are on the south side. The large glazing areas are on the south side. And you can even see that they've made holes in the roof, probably with glazing above, to allow more sun to come through that overhang and reach onto the terrace and through the glazing. Now, also notice this building is mostly black. You would not want to do this in any climate, say, south of New York City, certainly, and I would say really you would need a cold climate to make this to make any sense. So, but in Denmark, makes a lot of sense. You know, whatever heat you're going to get, go ahead and absorb it with that dark surface and warm up the exterior skin. All right, we're going to talk about 4 kinds of passive solar systems. Each of these passive solar systems has several components. Each one is going to have a collection strategy, it's going to have a storage strategy, and it's going to have a distribution strategy. And we might even add that it has to have a summertime strategy of some kind. And that might include shading, ventilation, etc. So the diagram on the left is showing you that there's a relationship between the glazing area, the collection, in this case we're using windows for the collection, and the floor area. So that in all of these we're looking at ratios of one thing to another. Glass to floor area to mass area for storage, etc. So in the direct gain room, this is the simplest form where the building itself becomes a kind of heat exchanger. So the passive solar, or let's just say the solar radiation, comes through the glass in the daytime. Now at night, there's no sun, so we need to store that heat. So the radiation comes into the space and strikes a surface, gets reflected off, gets absorbed by all of the surfaces in the room, and the surfaces in the room are exchanging heat by radiant transfer with each other primarily. And then the mass, or the thermal storage, is absorbing that heat. And then at nighttime, we like to close the insulating shade, close the curtains, try to keep that heat from going back out the windows, because you remember that the windows have a high rate of convective heat transfer. That means they have a lower R value than the insulated wall. And we'd like to retain all that heat that we've collected. As the surfaces and the air temperature in the space start to go down, the building's losing heat to the cold night air. It's losing heat by radiation to the cold night sky. Then the mass itself, which has been warmed up during the day, begins to re-radiate that heat into the space and into the other surfaces. So the collection is windows, the storage is a massive material such as brick or concrete, and then the distribution is simple passive radiation, no mechanical systems involved. And that's direct gain. Here is the simplest version of a direct gain building, almost that you can imagine. The building becomes like a thermal diagram. This is by the architect James Lambeth. It's a simple little cabin in Arkansas. You can see that it opens up in plan to the south, and it opens up in section towards the south also. So maximizing the facade, which has the ability to collect that solar energy, and then minimizing, in a way, the floor area that that glazing is serving. So a high ratio of collection surface area to floor area. The structure of the building is a massive concrete floor, simply a slab on grade. Ideally, some portion of that, at least on the edges, would be insulated. And then they've also got some some masonry, as you can see in that back wall. So really simple strategy. These are all examples that you can find online if you do a little search for passive solar heating, and you can begin to distinguish the south-facing glazing areas. You can see that most of them have some idea of shading in the summertime. So there's a big overhang in the upper right. On the upper left, you can see a series of louvers that can be controlled, and so on. So one might say that this building on the lower left, for instance, has a wooden floor and a lot of glazing. So the question might be, how are they doing the thermal storage? And that's one thing that you always have to remember. If you have a lot of south-facing glass and you have lightweight construction everywhere, then you have a real potential for overheating the building. This is Frank Lloyd Wright, 1948, the second Jacobs house in Wisconsin. And has a lot of the archetypal aspects of a direct gain building. So the building is curving around, right? That glass facade you can see on the lower left, that's facing south. And so it exhibits that variability that's possible in the orientation. Doesn't have to, every pane of glass is not facing true south. And it's picking up some heat by doing this all throughout the day. It's also carved out, so there's a kind of sunken garden area that you can see on the lower left. And then that earth is used to help create a berm, and it gets piled up on the north side, which you can see on the lower right. You can see on the upper images, this is a plan of a different house that was never built. That was used, basically derived from the same idea of the Jacobs house. So on the north side, very few windows, right? Earth berming, protecting from the wind, adding insulation to that north wall. On the south side, double height glazing with, you can just barely see through the glazing there. There's full height curtains that can be closed at night to help provide some extra insulation. The one thing that Wright didn't have that we have today is he didn't have really good access to great insulation. So there's a super high mass, super high glass. So there's a lot of loss, heat loss, there's a lot of heat gain, and there's a lot of heat storage. But that back north facing stone wall is still not very well insulated. And so it's also losing a lot of heat. But super thermal stability, no potential for overheating in this house with a concrete floor and a massive stone perimeter wall like that. You can see that the upper level is open. It's kind of like a mezzanine. And so any heat that's captured can be, shared between spaces in this house. And here's what it looks like today. Elegant edge on the north side. Trees have grown in. Right, and that characteristic earthy tone of the concrete floor that Wright likes to use. These are also direct gain passive solar buildings. So on the lower left is the German entry that won the solar decathlon competition a couple of years ago. You can see that on the upper right, a kind of conservative cabin-like architecture. The point of this is that we're really looking at proportions, we're looking at materials, we're looking at ratios, looking at how the building performs. That can be expressed stylistically or aesthetically in many, many different ways. Second system, call this a Trombe wall. Trombe wall is the more common term. That really means that the wall is using masonry as its thermal storage. The more generalized and accurate term would be a thermal storage wall. That's what the strategy is called in Sun, Wind, and Light. This is an indirect gain system. I said it's a Trombe wall if we use masonry. If we use water for the thermal storage, then we could call it a water wall. And I think I have some examples of that somewhere in the project here in the presentation. The thermal storage wall is simply a wall of masonry, right, which tends to be about 9 inches to 12 inches thick, and then an airspace, and then a layer of glazing. So solar radiation comes through the glazing, it hits the masonry wall, which is usually painted dark or coated with an absorptive surface that will help to absorb but not re-radiate that heat. And then slowly the heat moves through that wall. And it takes, hours, right? Maybe about an inch per hour approximately for the heat to transition from the sunny side over there to the interior side. So it has as some advantages that it's very stable. And it has some delay. So it doesn't, like a direct gain room would start to heat up early in the morning. This is never going to overheat early in the morning, that's for sure. It's going to deliver its heat later in the day. Right? So, but nevertheless, the size of the glazing here is really proportional to the size of the wall, not so much to the size of the floor. But we want to make the size of the wall still work relative to the size of the floor. So in the diagram, it has the whole wall. It doesn't have to be the whole wall. This is a nice house by Kelbaugh and Lee. This is in New Jersey. Kelbaugh went on to be the dean at Michigan, among other things. And you can see in the plan that kind of thick edge and the angled wall that's facing a little bit towards the southwest, actually. And it's facing towards the southwest, I believe, because that's the direction that the street was facing. So the architects here by the 1980s, let's say, are really starting to look at combining the solar heating systems with a range of architectural criteria that are not just about making the building as a thermal diagram. They're interested in performance, but they're also interested in the aesthetic and formal possibilities that come about when you're engaging the climate, when you're engaging the sun, and how the building is performing. And so on the axon, you can see on the upper right that that Trombe wall, the masonry that's behind that facade, is in sections. And it's alternating with windows. So the windows in between and the windows above the mass are actually direct gain. And then the mass itself is punctuated with some other openings. So really, you might say that whole wall is a combination of a direct gain and a thermal storage wall. And even over there on the left-hand side of this upper right axon, that's a sun space. So that the building actually has three systems. We'll talk about the sun space in just a minute. This is a building by the German architect Thomas Herzog. It's a youth hostel. You're looking at the southerly facade. This is a combination of Trombe wall. You can see the semi-opaque, semi-transparent sections alternating with glazed areas. So it's a combination, again, of a thermal storage wall and a direct gain. Up on top, you can see solar hot water collectors that are making hot water for the showers and so forth. This is a unique kind of a project. Illustration on the upper images of the south facade. Lower left is showing you the north facade. Again, more insulated. Really just having enough glazing there for daylight, maybe the occasional view window. On the lower right is a detail from the section in Sun, Wind, and Light about thermal storage walls. So if you just kind of go right to left, you can see the glazing. The glazing then behind that's an airspace. Inside that airspace is a roll down insulating layer and reflection layer. So that would be rolled down at night. It could also be rolled down during the summertime to reflect the sun back out. Then there's an interesting intermediate layer with those little horizontal lines. That's a transparent insulation material made out of thousands of little glass rods. It has a pretty good R value, so it insulates, but it also transmits light and heat. So kind of interesting. Then behind that you have the masonry layer, and that's doing the thermal storage. And then again, the primary distribution system here is by radiation. You can also have a vented Trombe wall to vent the space in between the glazing and the thermal storage, or between the glass and the mass, if you will. And if you've got vents coming, then, low and high, then that's a vented Trombe wall, and you're using some natural convection, usually, to help to move that air as the warm air builds up inside the cavity. So it could be radiation, it could also be convection. I'm going to just take a little break here and give you guys a moment to pause. If you want to come back, we'll pick up with this in part 2.